test. Okay. Okay, so everything should be working fine now. Good afternoon, everyone. So today we will be continuing on with our work and energy chapter. We are in chapter 3, and then later in the second half we will do the tutorial questions. And for tutorial 2, right, I believe there's only probably 2 challenging questions left, and then we will probably spend most of the time solving those questions, and then after that we'll see how much time we have left. Either we go back to the lecture or we continue the other tutorial 2 questions. Okay, so let's see. And before I forget, right, I pasted a announcement here, and also I announced in the Moodle as well, is that there will be a LaTeX class that is conducted by Dr. Darren Ong from the math department. So does everyone know what LaTeX is, or LaTeX? It is a software that you use to write documents, and every physicist and every mathematician at some point will eventually use LaTeX. Okay, so for example, right, all the lecture notes and the tutorial, everything I type out using the LaTeX, because if you try to do this using Microsoft Word, right, generally you ask any physicist or mathematician, if you try to type equations using Microsoft Word, they will look more ugly. And if you try to type equations using Microsoft Word yourself, it might be very troublesome and very tedious, right? So editing equation on Microsoft Word is a nightmare. So this is why people use LaTeX. And LaTeX is a specific type of software that is kind of like you need to know the codes and commands. So that's why you will learn like all these kinds of things. Dr. Darren will teach you the basic of how to use LaTeX. So this one is only for your interest. If you are interested, right? If you are interested, then you can join in the meeting on Friday. It's 3 to 5 p.m. So but otherwise, just to let you know. Okay, and I believe he will record it as well. I think so. I'm not sure. Maybe you can ask him, and then you can watch the video later if you want. So besides that, yes, I think now let's continue on with our work and energy. So for the we have stopped our work energy theorem until last time, right, which is here, the one-dimensional case. So, and of course our motion is in 3 dimensions, and so now we want to work out how everyone is how we deal with the 3-dimensional case. So everyone is okay, right? Am I online? Because I don't know whether no one respond or whether I'm disconnected. Yes, okay. Yeah, just to double check. Yeah. So let's go to full screen. Okay, then let's start with the 3-dimensional case. So now we want to talk about how to calculate the work done in the 3-dimensional case. And in 3-dimensional case, our force could be in any direction, so we give it in a vector notation, and our displacement as well could be any direction. Okay, so how do we derive the work energy theorem in this case? So for this case, we still use the Newton's second law. So according to Newton's second law, F is equal to mass times acceleration. So the force is equal to mass times acceleration, and then this is dot product with dr. Okay, so hang on, let me fix the lighting. Okay, and it is a good, okay, so from now, so it is good to practice how to use vector notation from the beginning, because you will be using a lot in other courses in physics as well, right? So this is why I always go to 1-dimensional and then 3-dimensional case. So how do we deal with the 3-dimensional case, right? For any direction, for any vector, this is an acceleration vector. So we remember that acceleration vector, right? Acceleration vector is the rate of change of velocity. So this is acceleration is dv dt. Okay, so then we need to express what is this thing in terms of we need to change variables, and remember what we want to do. When we did the first 1-dimensional case, right, we change variables into integrating velocity. So we want to do something similar here. Okay, so the way we can do it is, okay, so remembering that A is dv dt, Therefore, A dot dr is going to be this thing, right? So A dot dr is going to be dv dt, and then dot dr. Okay, so this is dot dr, and then what I'm going to do is, firstly I will change this. Okay, so I will add a dt over dt over here. So I got this, and then the dr is actually dr over dr dt with respect to dt. Okay, so this is the chain rule, right? So chain rule, and then after that, what I'm going to do is I'm going to swap places with the two of them. So dr dt goes to the front, and then I have dv dt over here. And always remember, right, we're talking about vectors, so we have to keep track where is the vector, where is the scalar. So this whole thing at the end is a scalar product, it's a dot product. So vector and vector together must have a dot product somewhere. So I'm just changing the order of the dot product. You still get the same answer like this. And then we realize that this is actually dr dt, this is just the velocity vector. And then this is dv dt dt, so this is the changing variable, it's just becoming dv. Okay, so from here we conclude that A dot dr is equals to v dot dv. So I have converted everything in terms of velocity now. So therefore I can I can try to work out this integration. Okay, so what is v dot dv? If you are not used to vector, dot product just means that the x component with the x component together, then you add with the y component with the y component together, and the z component with the z component together. So this is what it means when we have a dot product. Okay, so so this one is, we have now expressed everything in terms of a velocity integration. So this is mv dv. Okay, so this is mv dot dv, and I was saying that v dot dv is equals to this whole thing. So yeah, I can just write everything out. Okay, so this is just opening up the brackets. I got the x velocity integration, and the y velocity integration, and the z velocity integration. So vz, integrate this with respect to vz, and then we put in the limits of integration. So let me say that for this situation, my initial velocity is, let's say I call this v1. Okay, so v1 has x, y, z components, right? So we got v1x component, and then v1y component, and then v1j component, which is z. Okay, and then final velocity is the same thing. Okay, so which is v2. So we got v2 in the x direction, v2 in the y direction, and v2 in the z direction, 2z. K. Okay, so the last letter is k unit vector. Okay, so then this is how I put in my limit. So this is v1x until the final velocity v2x. So v1y, v2y, v1z, v2z. Okay, so these are just putting in the components, and then once you work out the integration, you just have half m. Okay, and then we got this integral, you got half, right, and then v squared. So this is the final x velocity squared minus the initial x velocity squared, and then similarly you got the half m final velocity in the y direction minus initial velocity in the y direction, and the z direction as well. So v2z square, v1z square. Okay, so so remember what we're trying to do. We are trying to show is that work energy theorem also holds for 3 dimensions. Therefore I want to express something in terms of a kinetic energy in the initial stage and the kinetic energy in the final stage. So all the initial values I want to put together in one term, and all the final values I want to put together in one term. So what I have now here is that this is v2x square plus v2y square plus v2z square, and then all the negative terms are involved in the initial velocities. So what I have here is v1x square plus v1y square plus v1z square. Okay, so the reason why I went through all this is to show you that this is also something that can be expressed in a more shorter way if I use the vector formula, right? So this is actually the final velocity dot product by itself. This is the initial velocity dot product by itself. So it's basically just the final speed square. This is the initial speed square. Okay, So what I have here is that half m, and then v2, maybe I shall say this. Okay, so half m b1 square. So you understand what I'm saying, right, when I do this? Okay, so dot product square is the same as the magnitude I shown you in the first lecture, right, chapter 1, when we were first talking about three-dimensional vectors. Okay, so now what we can do is we define the kinetic energy. Okay, so kinetic energy, right, so for a particle or object of mass m, and then moving in velocity v, therefore the speed is v is just the modulus v, right, and it's just the square root of the v dot v itself, right, has kinetic energy defined by k, which is just half m v square. So this v is now the speed square, or another way I'll say is v dot v. Okay, so which is why we have all this expression. Okay, so from here what we have here is that the work done from this calculation, right, in other words, what we have here is work done is the kinetic energy at the end of the process minus the kinetic energy at the beginning of the process. So at the end of the day, we still have our work energy theorem. Okay, so the work done is equals to the change in kinetic energy, right? So should I, yeah, so let me draw the box. Okay, and also let me summarize. This is what this equation is saying is that the work done during the process is equals to the change in kinetic energy. So this is the again the work energy theorem, but in any three-dimensional motion. Okay, so the work energy theorem holds for any three-dimensional motion for any object at any initial position and any initial velocity. Then you move to some other direction, right, and then have some final velocity. So what is the work done during the process? It is just a change in kinetic energy. Okay, so clear? Hopefully everyone clear so far? Okay, so if everyone is clear, then let's go to the next part. Okay, now we talk about power. Okay, so power. Well, people say with great power comes great responsibility, but this is over here. Over here, what we end up saying is that with power is just force times velocity. Okay, so power. Okay, so this is related to the concept of something like work, but power is the rate of doing work. Okay, so for any process, you can find the final kinetic energy and then the initial kinetic energy, and then you take the difference, then you can find the work done. Okay, so that is like that is just the total work done. Right now, we want to see how fast this process will take place. Okay, then that is the power. So this is the rate of work being done. Okay, yes, of course. Yeah, Spider-Man. So who's your favorite Spider-Man? There are now, in our lifetime, right, I think there are 3 different actors playing Spider-Man. So there's so many Spider-Man movies by now. So, but for power, okay, is what I was saying, right, is the rate of work done on an object, and we define it as the letter P. Okay, so the letter P is the rate of work done dt. Okay, so the formula is dw dt, and I will derive a second formula based on this definition. And actually, seems like the question I saw most of the time we use the second formula more frequently than this one. This one not very convenient because this one work done change in kinetic energy, not then, but what we really want is the how much energy is being transferred. Okay, so yeah, so let me derive the formula first, and then I will make more comments about it. So let's start with the work done first. Okay, so recalling the definition of work done is the integral of f dot dr. Okay, so everyone should be okay with this by now. And we change variables again. Okay, so now we change variable. I will keep f at the moment, and then I will purposely change this into a t integration. So instead of integrating with the r variable, I integrate with respect to t, the time. Okay, so this is the r dt, and this one is the r dt is recognized as the velocity. Okay, so what we have here is that we got f dot v, and then integrating this with respect to dv. Okay, so this means, right, so this means that w is the integration of dt, so which is to say that we conclude that this is something that you learn in the calculus. What is the opposite of integration? Differentiation, right? So that means this is the differentiation of w, or in other words, f dot v is the antiderivative of w, which is to say that dw dt is f dot v. Okay, so f dot v, and dw dt is what we define as power. So power is the force dot velocity. So for any particle in motion, right, you can figure out what is the force acting on that particle, and then if you can get the velocity, the dot product will give you the power. So of course this is the instantaneous power, because at different moments in time you can get different force and different velocity, right? So this is just to remind you, this is an instantaneous formula. Power. Okay, so power is instantaneous, right? It's not the total number that you get over average from beginning to end, like work done, but it's something has a number at every moment. Okay, so yeah, let me see if there's any question. With great power comes great force and or velocity. Yes. So Kaheng likes the last one with the cool suit. You mean the Tom? What's his name? Tom Holland, the young kid, right? Yeah. So I have not seen the last one. Have I? No. Yeah. Never mind. Yeah. So with great power comes force times velocity instead of great responsibility. It still rhymes. That's interesting, right? So what I was going to comment is that, yeah, it's about energy. Okay. So we will learn. We will talk more about energy later. We already talked about kinetic energy, right? So kinetic energy is the changing of kinetic energy is work done. And then after this, I'm going to talk about potential energy next. So what we learned here is that we got energy, right? And then energy can transform into one form or the other. And the W seems to be giving us the changes in energy. Okay, so our interpretation is like this. We have the concept called energy in physics, and then work done is something that captures information about the changing of energy, right, or transfer energy. So for example, if an object, right, if a mass can accelerate from 0 to some velocity, the kinetic energy increases. Okay, so the change in kinetic energy is the work done. Because this is changing energy, the work done is how much energy you transfer into an object for it to accelerate until you get this final kinetic energy. So the work done is the transfer of energy of the system. So that is the work done. And then power is dW dt. So the power is the rate of energy transferring into the system. Follow so far? Okay, so so all these are words, right? Work, power, energy, force. Before, outside of physics, they are just like general terms. You know, we're not really. But here has specific meaning, right? So energy is something. Okay, the work done is transfer in energy, and power is the rate of energy transfer. How fast you can pump energy into a system, or how fast an engine can extract energy from a system, and that kind of thing. Okay, so power is a important concept, especially when you talk about electrical circuits and design and things like that. So that's why when you plug in your electrical supply, right, they tell you the power. So because they want to tell you how much electricity can flow into your device at a given time and how much energy you consume. Okay, so so that is power, and it is a new physical quantity. So I should talk about the units. Okay, so what's the unit for power? So let's look at it this way. Okay, so the power is the unit for dW dt. Okay, so dW dt, right, is the same as the unit of the changes in W and the changes in dt, right? dW dt is just the limit of, by definition of calculus, is this. So in other words, it's the same unit as work divided by unit of time. And what was the unit of work that we talked about last time? It is the ml squared t minus 2, and then time is another t down here. So the unit of power is ml squared t to the minus 3. Okay, so from here we can get the SI unit. So the SI unit is kg, and then a length square, so we put meter square, and then second minus 3. And this unit, normally we call this one watt. Okay, and sometimes in your electrical supply they say kilowatts or megawatts of power and things like that. So this is how much energy exactly we are talking about. Okay, so and also another way of saying is 1 watt is joules per second. So joules per second. Okay, so watt, or JS minus 1. Okay, and I try not to use W lah, because W also we say is work, but so happen this scientist named Watt, so it's also W, and to avoid confusion I just say watt in full. Okay, so let's say watt. Okay, so this is the unit of power. Okay, everyone clear so far? About the end of energy, since we don't have natural phenomena that convert heat to other type of energy, all energy exists as heat. You're talking about the heat death of the universe, right? That's right. So this is what you I believe you are learning. Maybe thermodynamics will talk about this a bit. Is to say that yeah, so what Kai Heng is saying, right, everyone else, is that energy, yeah, so I'm talking about different types of energy: kinetic energy, later potential energy, and they transform to one form of energy to another. Okay, but then in your thermodynamics course you will learn about the second law of thermodynamics. It says that some transformation can happen in one direction but cannot transfer back. Okay, and that has to do with the increase of entropy. So according to the second law of thermodynamics, every physical process must obey the second law, which is to say that any process must result in either net increase in entropy, or the best is maybe zero change of entropy. Entropy cannot decrease. So apparently any form of energy converted into heat must increase in entropy, and the backwards transformation must decrease entropy. So it Kai Heng's question is that, yeah, energy always, everything is being transformed into heat. So that is a very problematic situation, because if everything can transform into heat and cannot change back, then that will be the end of our universe, right? So, and in our universe, all the physical process happens and takes place, but more and more changes. If more and more things accidentally got changed into heat, cannot change back, so more and more heat accumulates, right? And then once everything changes into heat, there's no more physical process that can happen, and that is how the universe might end. So are there ways to convert heat into other energy? That is Kai Heng's second question. Yes, so that is in the derivation of the unit. Wind driven generator is is good example of heat into energy. Okay, so I'll talk about the unit again, and then I'll answer the other question after this. So how to figure out the unit of power, right? Actually there's two ways. I was looking at it as this. So the unit of power is the unit of dW dt. So what is dW dt? dW dt is basically just is a unit of work divided by time. Okay, because dW is a infinitesimal change of work, dt is an infinitesimal change of time. Okay, but in units wise, it's basically work energy divided by time. So it's joule divided by seconds. So actually that's all. I make it more complicated by writing all this, but actually it's just energy divided by time. Okay, so actually that's all. So yeah, so I think does that make sense to Charles? Then there are ways to convert heat into other energy, but yes, you will learn in your thermodynamics course is that you need to make sure your process has a net increase in entropy. Okay, so where's like for conservation of energy, right? So total energy, that is what we are learning in this chapter, right? So total energy of the universe is conserved. Actually, total energy of the universe is not conserved, but that's a different story, right? That one is like is a cosmological model, but for now, let's say total energy is conserved, right? And then so you can say that let's say we got heat, and then plus some other forms of energy. I don't know, just randomly electrical energy. Right, so you can convert this into other types of energy, right? So maybe kinetic. Okay, and then but generally we expect to have some amount of heat. Okay, so any process is allowed as long as your change in entropy is greater or equal to 0. So yes, there are ways to convert some a mixture of heat and other energies into this kind of thing, as long as your entropy is conserved. Okay, so there's 2 layers to your question, and heat actually, if you focus on a subsystem, right, what I'm imagining now is a refrigerator, okay, or a room is an aircon. So if I look at a refrigerator inside a room, then maybe the total heat of the total system will increase. But if you just look at a subsystem, right, the refrigerator itself, right, so refrigerator itself, you convert, if you just care about this refrigerator, then it looks as if the total heat is decreased. You are pumping heat out of your system. Okay, so if you focus on subsystem, then yes, you can violate the thermodynamics, because the total system, the rest of the universe will make sure it's obeyed. So it's actually a tricky way to answer the question, because some people might say, if you just talk about refrigerator, then yes, heat can decrease, but this law is supposed to apply for the total universe. So as long as the total universe have net increase in heat, then still yes. Okay, so wind driven generator is difference between air and wind can cause it. Yes, so for Kahing is right. So Zuri's example of wind, right, the wind is kinetic energy of the air. So the air molecules have kinetic energy, and then air collides, and then kinetic converts to electric. Yes, and then so it because not everyone is taking thermodynamics, right? Or the physics student, yes, the math students no, but so never mind, so don't worry about it. Okay, so, and in fact, if you don't take thermodynamics, right, I'm gonna make it more confusing. Kinetic convert to electric, yes, but actually in thermodynamics, right, if you actually look at the air molecules and particles, the temperature of a system, maybe you learned in high school already, temperature of a system is actually due to the kinetic energy of the molecules. So this is like, this is kind of like heat energy, right? It's associated with some temperature of the system, and then so you interact with the wind turbine, is you're converting a hot, thermal weather system, converting into electricity. Although another level you can say is kinetic energy converted into electric. Okay, so because we don't have to generate heat by either source of energy on purpose, yes, so the problem is, yeah, because of the second law of thermodynamics, then it's very difficult to convert heat into other forms of energy. Okay, because to convert heat into other forms of energy, to convert pure heat into pure kinetic, or pure heat into pure chemical or electrical energy, if you calculate entropy, most processes will violate the second law. Okay, it will violate this, but besides that, you know, that it is possible, but we need to find. Okay, so so Prof Ong just taught, right, heat energy is particles kinetic energy. Yes, yeah. So yeah, there's a simple formula to relate temperature to the velocity of the a simple formula to relate temperature of a gas to the average or root mean square velocity of the particles inside. Okay, so yeah, why are we talking about thermodynamics? This is a mechanics course, right? So let's talk about mechanics. 3.2.1. So we have, let's work out an example. So let me show you the notes. Okay, let me bring this up. We have reached until power already. So we want to solve this example. Velocity of an object of mass given by this formula. Okay, and the power, what is the power due to the force on the object, in particular when t is equals to 2 seconds, and then the mass is given as 3.0 kg. So let's try to solve this. Okay, bring this down, put this back. Let's try to solve this. Okay, so for this problem, we are talking about, well, it's a one-dimensional motion. So let's call this direction x. So assuming motion along the x direction, right? So my velocity, right? The question gave you the speed or the magnitude is alpha t, and then if I use a vector, I must put the direction, right? Most of the time I purposely write things as vector, even though we don't have to, but I just want to let everyone practice the vector notation, because seems like yeah, not everyone is used to it yet. So the more I write, the more practice we get. In any way, we want to calculate the power, right? So I forgot what the question says already. We want to calculate the power on the object. So I will use the formula of F dot V. Okay, so F dot V, well, first of all, I need to calculate F, right? So F is equals to mass times acceleration, and I know the V. So if I can figure out the acceleration, I can get F as well. So the acceleration is the differentiation of V. Acceleration, right? So acceleration A is just differentiating V with respect to time. Okay, so that means I just need to differentiate this with respect to time. So I got alpha times I. Okay. By the way, alpha actually in this question is 2.0, right? So it's a number, but I want to keep it general. Okay, so it's a number, it's a constant. And anyway, the from the acceleration I can get the force. The force is mass times acceleration, so it's just m times alpha times I. So the power is P is equals to force dot product with velocity, right? So power is a scalar quantity, right? But I can calculate this using two vectors by dotting the products. Okay, so I got m alpha in the vector I, and then the velocity is alpha t in the vector I. So from here I got m alpha square I dot t. I dot I is just 1. So this is my general formula for the power. So according to the question, the mass of the object is what? 3 kg, and then alpha was 2 square, so it becomes 4, and I want to calculate what happens at 2 seconds time. So 6 times 4, so it's 24. So the answer is 24 watts. Okay, clear? Everyone clear? So I should let you look at it for a while. And let me check your questions on my phone. Kaheng said never mind about what? Not anymore. Okay. So yeah, so this is a simple calculation to our question. Right? Clear? Everyone clear so far? Does anyone have any question? Not a mechanic class anymore. Oh yeah. I was talking about that just now. I see. Yeah. Yes. Mechanics and thermodynamics. Why is A is alpha I? Well, so you, Charles, you agree that velocity is given by this formula, right? This is the velocity. So acceleration is differentiating t. So alpha is a constant. Alpha is actually just 2. But yeah, so actually I could have just write 2 here. So if I differentiate 2t, I just get 2. Right? And then this is just to tell us the x direction. You know? Okay. So yeah, so it's just acceleration is the differentiation of velocity. So that's all I'm using here. Okay. So this is page 3. Anyone has any other question? Page 3. Okay. So speaking of Spider-Man, right? The second movie of Spider-Man, the one with Tobey Maguire, Spider-Man 2. There's a part where he attends a quantum mechanics course, which is a course you, the physics student, right? Most of you guys will take next year, and then there's a scene where after you've gone through the course, I think after you've gone through QM2, maybe you will recognize what the Spider-Man lecturer was talking about in that scene. He's talking about the Stark effect, the energy eigenvalue, and then in another scene, right? You can see him carrying a textbook, which is quite a famous QM textbook, which some of you might be using. If I believe it's Sakurai textbook. So the Tobey Maguire Spider-Man is taking physics in those movies, the Spider-Man 2. So yeah, we're gonna go to the next topic now. Okay, so 3.4, potentials and conservation of energy. Potentials and conservation of energy. Okay. Sandman is Spider-Man 3. Yeah. So the previous movie. Yeah, you can review the movie if you want. The Spider-Man 2 with quantum mechanics one is he fight the, was it Octopus? Yeah, I think it was Octopus. The Dr. Octopus. Okay, so 3.4.1, conservative forces and potential energy. Okay. The Spider-Man 3, I think everyone says it's no good. I watched also, it wasn't that fun. Okay, so so now we want to talk about potential energy now, right? So what we have learned in this chapter is we start with work, and then through work energy theorem we define kinetic energy of a system. So kinetic energy is energy associated with the motion of an object. Okay, but then when the object stops moving, right, we come to a situation where it has what we will call a potential energy. That means This one is very common. Like the word potential sort of tells us what this energy is about. So even if an object is not moving, right, it has a potential to move. That's why we call it a potential energy. For example, you have a spring, right, for a loaded spring. So if an object mass attached to a spring, and then if I stretch the spring, okay, so if I stretch the spring and then I don't move, nothing is moving. Okay, nothing is moving means no kinetic energy, right? But I know that if I let go of my hand, this object will snap back with very high velocity, which means that this is going to have a high kinetic energy, but not yet. Okay, so it's going to have a kinetic energy, but at the moment not yet. So same thing for gravity. So you have an object, right? Okay, like if I move object to a very high position, okay, right now this object is not moving, right? So right now it has no kinetic energy, but I know that if I let go of this thing, it's going to fall down. So I know that if I let go, it's going to have kinetic energy, but that's later, right? So it's going to have kinetic energy later. So right now, where is the energy now? Okay, now we learn about, right now it is in the potential energy of the system. So this is the concept of the potential energy, right? So right now it's potential energy, right? It's energy stored in the physical, the mechanical system, right? And then if I let go, it will convert into kinetic energy. Kinetic energy is moving, so that's kinetic energy, right? So this is what we want to talk about. Okay, so far from home. Oh, far from home is the latest one, right? Okay, fake fan. Yeah, potential energy. Yes, so that's the potential energy we are talking about now. Oh no, Homecoming is the first Tom Holland one. Far From Home is the sequel, right? And I think Far From Home is the one I haven't seen. So we consider a one-dimensional. First, let's talk about one-dimensional motion again. Okay, I think for this chapter, we confine to one-dimensional motion for potential energy, because for the physics student, to define a 3D case, you need to learn multivariable calculus first. And you will learn more on the calculus tool, right? MAT students know what I'm talking about. Maybe not yet, in the later line integral section. But for now, we talk about one-dimensional motion of a particle. And it's under a force F. So let's call this force F. Okay, and then as usual, we know the formula for work done. It is given by the integral of F with respect to dx. So we're only talking about the x-axis now. Okay, so in order to define a potential, right, this is the important thing. Okay, we need the force to be a function of position only. Okay, so if F depends on x only, okay, if it depends on other things, let's say a time dependent force, then we cannot continue. But our discussion requires F to depend on x only. Okay, or constant, fine, but at most depends on x only. Okay, and the antiderivative exists. Okay, so if it's a function of x only, then we can imagine integrating this function. So the antiderivative of f exists. Okay, for example, right, in other words, which is to say that there exists a function we call hx such that dh dx is equals to f. Okay, so if everything is a function of x only, then I can differentiate and integrate them. Then I can say this. Now, if only this is true, then I can calculate the work done, right, by using the fundamental theorem of calculus. So if I'm integrating with respect to x, I imagine I have some initial position and some final position, right? And then the integral of f is the function h. So this is h, right? It's a function of x, and then from x1 to x2. So this is basically the function evaluated at x2 minus this function evaluated at x1. Okay, so this is some function hx. Okay, so this is where we can define our potential energy. So our potential energy okay, is defined as the negative, how to say, it's a function which we call u, and is defined to be a negative antiderivative of x. So let's just say, yeah, it is the negative plot times the antiderivative of x. So antiderivative, what time is it now? Okay, it's still early, of f, and then we call it u. Okay, so normally we call it potential energy u, and it's a function of x, right? So in other words, what we have here is the negative antiderivative of x. That means if I differentiate u with respect to x, okay, and then put a minus sign over here, I will get back the expression for the force F. Okay, so the negative, why we put a negative sign here, is just convention. So in the context of above, right, this is just negative hx. Okay, so I attach an extra negative sign, and the one with the negative sign is what we call the potential energy of the system. Okay, so so that means let's calculate the work done in this situation. So in this case, what happens to our work done? Okay, so in this case, what am I talking about? In this case, that means f is negative du dx, right? So the work done is the integral of f dx, right? So from x1 to x2, okay? So if I integrate already, I get minus u, okay? It's going to be a function of x, right? And then I evaluate from x1 to x2. So the negative sign might be very confusing and might cause problems. So this is where we have to be careful, right? So let's try to be very careful with the negative sign. So it's negative u calculated at position x2, then minus negative u calculated at position 1, right? So there's a plus and a middle. So this is minus u x, and then u x at 1. Okay, so since there's so many brackets, I'm lazy to write, so I'll just call this the potential energy at u and the potential energy at 1. Okay, so from here I got the result that the work done is equals to potential energy at position 2 plus potential energy at position 1. Okay, and then remember what we were talking about on the left hand side. We had the work energy theorem. Okay, so by work energy theorem, okay, we have calculated this to be the change in potential energy, right? So the change in potential energy, so this is change in kinetic energy. Work energy theorem is the change in kinetic energy. So I got K2 minus K1 is equals to minus U2 plus U1. Okay, so from here we there are two ways to express this equation. Okay, so two ways to express this equation. To express another way, in other words, two ways for us to remember this equation. Okay, the first way is the way that I always remember since I learned this in the high school, is that if I move all the 2 to the left side, okay, so I got K2 plus U2 is equals to K1 plus U1. Okay, so what is this? This is the kinetic energy at the final position and the potential energy at the final position. Then this is initial and initial. So this is everything, all the total energy related to the final situation. This is all the energy related to the initial situation. So in other words, what I'm trying to say is that this is the total final energy is equals to the total initial energy. Okay, so E2 is equals to E1. So final energy is equals to initial energy. So this is the statement of the conservation of mechanical energy, right? So so actually I'm a bit loose with the language. What I should say is we are talking about the mechanical energy. Okay, mechanical. Because there are other types of energy. We were just talking about thermodynamics, right? Heat energy, and then if you take any chemistry course, there's a chemical energy, chemical potential, you know, all those kind of things. And then in the next semester, the next semester, you learn about electrical energy, magnetic energy. So this is mechanical, right? So this is where I should probably define more precisely. Mechanical energy is, when I talk about mechanical energy, at least in this next few chapters, okay, is the energy E. It is the kinetic energy plus the potential energy. Okay, in fact, it's the total potential energy of the system. Okay, you can have different types of potential energy. So E is equals to K plus U. Okay, so this is our mechanical energy of the system. So this is the first way I remember this equation. Okay, so this is how I remember this. The second way, I don't know whether you will like it, is well, look at this is K2 minus K1, right? And then there's a negative, there's a plus. So if I pull out the minus sign, I have a U2 minus U1. So some people prefer to remember things as a change. So this is the change in kinetic energy, and then this is a negative change in the potential energy. So this is, from here I got this equation, delta, if I bring this over, I got delta U plus delta K is equals to 0. Okay, so of course we have defined this is the mechanical energy already. So this is the change in the potential plus the kinetic of the system is equal to 0. So this is the change of the kinetic energy, total initial energy of the system. So what this statement is saying is that total mechanical energy doesn't change. Okay, and both, whichever way you are remembering this, is it just means the same thing, right? This is our conservation of energy. Well, more precisely, this is all the energy we're talking about here is mechanical energy. So this is the conservation of mechanical energy. Okay, so this is where you learn, like in the high school, will teach you that energy cannot be created or destroyed because the total energy of the system, it may change. Okay, so what we find here is that even though the total is fixed, but you can convert from one form to another, right? So the K alone doesn't necessarily always have to be the same. The U alone doesn't necessarily always have to be the same, but the total sum must be the same. Okay, so maybe you have something with a high potential energy, and then later you convert to with a low potential but high kinetic, right? So they can transfer into one to the other, as long as the total energy of the system is always the same. Okay, so this is our conservation of energy derivation. What was it? Newton's gravity. A lot of things. Okay, wait, let's see where potential energy, must it exist in field? Okay, so I'm checking from the beginning. So Zurich said in a field, if you're talking about like a field, that means, yeah, so field here is like basically the force is a function of x, right? So the force is a function of position. So this is what it means in the higher level. It's called field. Field is that you have a quantity that is a function of position. So for potential energy, we learned that in respect to Earth, artificial black hole, the closer the potential gives a linear energy change. Potential energy. Oh, okay. I know what you're talking about, Kaheng. Kaheng's question is talking about potential energy for Earth. We actually calculate this later, right? It's mgh. Okay, so it changes linearly with position. But later we learned that actually this is an approximation. When we go to the gravity chapter, it will change inversely proportional. Okay, so it's not linear. For spring is also not linear, so it will not work as above. Okay. Yeah, so Zuri was saying what I was trying to say just now. So for mgh, the potential energy is linear. So this formula is valid when okay, either the constant g is too small or we are near the surface of the earth. But if we are far away from the earth, then no longer linear. Okay, so but artificial black hole. Okay, so yeah. So the what you're asking is actually we will actually address this in today and also the next few chapters. Okay, so it's not a constant. Yes, Zero is right. So yeah, so we will work out examples. Okay, where are we now? This is page 4. And what time is it now? Okay, so 4 more minutes. I should go a bit faster. Okay. Yeah. So since since Kaheng and Zero was discussing about this, right? Let me just jump to this. So let me define conservative force. Okay. So when we're talking about a conservative force, right? It just means that when forces where the conservation of energy is obeyed. Okay, so here we are talking about mechanical. Is obeyed. Okay, which means that, what do I mean? Conservation of energy. Well, conservation of energy is either total energy is fixed or no change, right? And how do we get this? Right, so how do we get all this calculation? Our starting assumption is that we need to have function f to have an antiderivative that is unique, so that the initial and final position, this value is unique. And the way for this to be unique is that f depends on x only. Okay, so f depends on x only. So this will happen if f is a function on x only or constant, right? That means it doesn't depend on other things. Okay, so this is what it means by a conservative force, right? It doesn't mean that this force is right wing or that kind of thing. Another meaning for conservatism, right? So so yeah, so since you guys are discussing this, let's work out some examples. Potential energy coming from conservative forces. Okay, so the first one that you guys were asking is about the gravitational potential energy. Okay, so gravitational potential energy is because of this, right? So the force due to gravity is the weight, right? So we call this F, gravity is equals to mg. So let's take negative mg and upwards positive. Okay, so this is our force. Now, this force is a constant for a fixed mass, is a constant times another constant, 9.8. So it depends on, it's a constant, so it doesn't depend on anything else, which is conservative, right? So then the antiderivative of x of f is this one, which put a minus sign, it will give you the potential energy. So this is f dy, right? So if I integrate this, it just gives you a mg times y, right? Mg times the height. Okay, so hang on, I must be careful. I mean, I forgot one minus sign, right? So my f here I take up as positive, so I put mg, this is a constant, integrate this with respect to dy, so I got a positive mg y. So my y-axis is taking upwards as positive. So if I take down as positive, then this will flip a negative sign over here. Okay, so Kaheng is saying, okay, is potential energy linearly dependent on position? Well, we got this formula is because my f is a constant, and I believe this is what Zero is saying. Well, the force of gravity here is constant. This is only true when we are close to the surface of the earth. Later in chapter 6, I think, the correct formula for gravity is this formula, right? So it's only when force is approximately constant near the surface of the earth, then is approximately a constant. We will actually calculate this in detail later. Okay, and then yes, let's double check. Yes, so yeah, so this is what you guys are talking about lah. So the formula is so don't worry about this. We will come back to this in chapter 6. Is it chapter 6? 7, might be 7. Okay, so the chapter on gravity. Okay, so this is the force of gravity is not a constant. The further away you go from the planet, the weaker the force is. But every day we are near the surface of the earth, right? Either you're on the ground floor or the first floor, just a little bit, right? First floor is just a few meters of change. Then your weight in going from first floor to ground floor doesn't change much. It's approximately a constant. So mg is approximation. Okay, so second force is the elastic potential energy. This is from Hooke's law. Okay, so for a spring, my F is negative kx, right? It's always negative to where your x position is. 0 is the equilibrium point. Then the potential energy due to the spring is the negative antiderivative of this thing. So we plug in the formula correctly. So we put in negative kx. We integrate this with respect to dx. The negative sign cancel. This is how you get half kx squared. Okay. So when at the equilibrium position, x is 0, so you got 0 potential energy. But if you stretch the spring, you will increase the potential energy of the system, right? And once you let go, it will turn into kinetic energy. Okay. So yeah. Any question? Any other question? Okay, so I think everyone is okay. So I think we dragged too long already. So let's take a 5 minutes break, right? 5 minutes break, and then we will continue on with the tutorials. Okay, yes, we will continue on with the tutorials. So let me stop recording. Stop recording. Thing to compare and contrast all the different changes. Okay, so I'm starting recording, and we shall do the tutorial. Test. Okay, so we are now. Let's do tutorial, and we stop after the pulley question until here. So this is the question that we want to solve now. So let me pull up the question. Okay, and let's look at it. So we have a mass of 40 kg slab resting on a frictionless floor, and a block of little mass m 10 kg sitting on top. There is friction between these two blocks. Okay, and the question gave you coefficient of static friction and also kinetic friction. Now that's funny. Why? So the block is pulled by a horizontal force F. And what is the acceleration if F is 100 Newton and if F is 60 Newton? So this is the situation where we have a static friction, but if the force is too strong, it will start to slip over the surface, right? So this is what we want to calculate. Okay, so everyone ready? Yeah, so I'm going to solve the tutorial now. I'm going to figure out the answer for this question now. So let's work out the answer. Okay, and I should probably draw the picture first, right? So we have this is question 9, right? So we have a slab that is on a frictionless surface, and this is big M. Okay, let me make it full screen. And then on top of it is a little mass m, and this is where the external force F is exerted on it. Okay, there's friction between these two surfaces. Okay, so how do we answer this question? Well, first of all, right, we need to know whether this is undergoing static friction or kinetic friction. Remember, static friction means what? Means that there's no relative motion. They are both sticking together and they are both moving together all at once. If that's the case, they have the same acceleration. If this is kinetic friction, then they are not moving together. Okay, so there is a separate motion with each other. You must calculate them as separate accelerating masses. So which is happening, static or kinetic? We don't know, right? So it depends on the F. If F is too strong, it will become kinetic friction, right? If you pull it too strongly, the top part will scrape over the bottom mass. But if you pull it softly enough, they are just moving together. Okay, so that means the first thing that we want to do is we need to find the range of static friction. Okay, so first we need to calculate what is the possible range of static friction first, and whether the F has exceeded the maximum static friction sustainable by the system. Okay, so everyone follow what I'm trying to do now, I hope. So that means my sound is okay, right? I'm online still. Test. I think I'm okay. Yes. Okay. So now we try to find the range of static friction. And to do this, firstly we shall assume no relative motion, and we solve it as a static friction. Right? If there's no relative motion, both blocks have same acceleration. Okay, so to solve this, well, let us do our usual method. We draw the free body diagram. So what are the forces acting on this box? So let me solve the upper object first. So let's draw the free body diagram for the upper box. Okay, what are the forces acting on this system? Well, first of all, I have a external force F. Okay, and then it is sitting on a surface. There's a rough surface, so there's friction. Right now we are calculating it as a static friction. Okay, and then of course there's a mg, and then in this case the normal force will be equals to mg, so there's not a problem there, right? So let's look at the horizontal forces. So for the horizontal forces, right, what is the net force? Now I take left as positive. Okay, so F minus the static friction this is the net force. So the net force by Newton's law is equal to ma. It's not zero because this system is accelerating, right? The whole thing will move. Okay, so this is my equation 1. Okay, so that is the first object free body diagram. Now let's look at the lower slab. So for the lower slab, what is the forces acting on the slab? Okay, the total mass is big M for this object here. Well, this is frictionless, it's smooth, so there's no force here. Okay, so the only force acting on this is because of the static friction between these two. So there's only a static friction acting on the top of this slab. So now let me ask you this question. What is the direction of static friction? Okay, so there's going to be static friction, but the direction is, well, it's going to be forwards. Do you feel it strange? Why is it forward, static friction? There's two ways to look at this. First way is, well, you look at Newton's third law. Both of them is sharing the same force. This is the action and reaction force. So by Newton's law, they must be opposite direction. Another way to imagine this is the slab, right? And this slab eventually will get dragged forward. There's only one force acting on it. So imagine that you are the slab and there's a box sitting on top of your head, and this box is being pulled forward and there's a friction. So the friction you feel is roughly feeling that pushes you forward. So the only force acting is to the left is positive Fs, magnitude is Fs, and it will result in mass times acceleration. Both have the same acceleration. Do you agree? Right? So if you agree, right, I can actually solve my system now. I'm going to take equation 1 divided by equation 2. So dividing these two equations, I got F minus Fs divided by Fs. If I divide these two, I will cancel the mass, so small m divided by big M, and then I can find the F in terms of little f. So if I solve this equation, I'm going to get 1 plus small m plus big M. bring here, you plus, yes, and then little fs. Okay, so I got this formula to relate static friction in terms of the big F. So the static friction, remember, is an automatic force. If I exert a small f, then static friction will satisfy this equation automatically. No relative motion, I mean, I don't know, not cancel in the opposite direction. I would say that this is the Newton's law, action and reaction. Okay, the static friction is like the lower slab exerting on the upper box. This part is the upper box exerting on the lower slab. So it's more like Newton's third law. Yeah, so that's the key point, right? It's not kinetic friction, because kinetic friction is kinetic motion, right? It's the rubbing action, right? If kinetic action is rubbing the surface, but this situation here is just touching, and then they're moving together. It doesn't scrape against each other, so it is static friction, no relative motion, right? Yeah. So the best way to remember kinetic friction is, if kinetic friction means it must be rubbing, right? If you rub, you will feel hot, right? But if you just touch, static friction, you do not feel hot later. Okay, so that's the difference between static and kinetic friction. But now we got this formula now, right? We can actually calculate the maximum force to exceed this static friction. So when F reaches a maximum point, then this static friction maximum point will be static friction times the normal force, and based on this, normal force is equals to mg, so N is equals to mg over here, so this one is straightforward. Okay, so we can actually calculate this maximum force. So my F maximum is equals to 1 plus small m plus big M, and then this is mu s, and then times the little mg. Okay, so if I can actually plug in the numbers. The upper box is 10 kg, lower box is 40. Coefficient of static friction is 0.6. The upper box is 10. G is 9.8. So if you put in the numbers, you get 73.5 newtons. Okay, so the maximum force is 73.5. Right? So now we can finally figure out what is happening here. Okay? So if I pull it with a force that is less than 73.5, smaller, between 0 to 73.5, then the upper box will stay fixed to the surface. Okay, but if I pull it with a force that is higher than this number is exceeded already. Higher than this number is too fast, is too strong, so it will be scraping over the surface. That means it will become static friction. Okay, so any force higher than 73.5, it will make it go static friction. Less than that, it will still become, I said the other way around. If I pull it with a force that is higher than 73.5, it will make it go kinetic friction, right? Rubbing. If I pull it with a force that is smaller than 73.5, smaller, then everything is still static. It will still fix to the surface and go. Okay, so hope everyone follow the story so far, right? So that's the difference between static friction and kinetic friction, right? So just because the system is moving doesn't mean it's kinetic friction, because it's still sticking together, so that's why it's static. Okay, so this is page 6. Now now it's just finding the maximum force. We haven't even started answering the question yet, right? So now we answer the question, part A. Part A is the pulling force is 100 Newton. So 100 Newton is greater than 73.5, which we just calculated. Okay, it's greater than this number. So greater than this number means it's too strong. If you're pulling it too strong, it will make it go kinetic friction. The upper box will scrape over the slab. Okay, so it will become kinetic friction. Kinetic friction means relative motion between the two objects, M and big M, which means that both of them have different acceleration. So both box have different acceleration. Okay, so now we can resolve this problem, but now we assume it's kinetic friction, because now we confirm there's definitely kinetic friction if we are pulling it at 100 Newton. So the weight is still the same, the normal force is still equal to mg. Right now we are definitely sure that if I pull it at 100, this is a kinetic friction. This is mu k times n, and n is equal to mg over here, so we can put it into here. Right, so we got 100 minus the kinetic friction is equals to the mass of an acceleration of the upper box, right? So 100 times mu k times n is equal to ma1, and n is equal to mg, so it's mu k mg is equal to ma1. I can actually solve this for a, right? So it's 100 minus mu k, kinetic friction is 0.4, the upper box mass is 10, and 9.8 divided by 10, so you will get 6.08 meters per second square. This is the acceleration of the upper box. Okay, now we go to the lower box. We draw this is the upper one, then we go to the lower one. Okay, so the lower one is the big slab here is on a frictional surface, so there's no force coming from here, there's only a static friction. So same reason as before, the friction is pulling this thing forward, but it's a frictional force now, drag for relative motion force, kinetic friction. So there's only one force acting on this upper box with this acceleration, and this friction we have calculated to be mu k times small mass times g, right? This is the magnitude of the kinetic friction, and then this is ma2, so a2 is mu k mg divided by m. So if you put in the numbers, you will get 0.98 meters per second square. Okay, so this is when they have, if I pull this at 100 newtons, both boxes have a different acceleration, right? They have different acceleration. The upper box is going faster than the slower one. Now, what if I pull this at 60 newtons? So if I'm pulling this at 60 newtons, 60 newtons is smaller than this number. Okay, so it's less than 73.5. So less than 73.5 means still static friction. Both have the same acceleration. Okay, so if both have the same acceleration, we can just treat this as one big object. One big object accelerating at a and being pulled by 60 newtons. So the F is equals to the overall system times the same common acceleration. So I'm pulling this at 60. This is 10 kg plus 40 kg and acceleration. So from here, the common acceleration is 1.20 meters per second square. Okay? Everyone follow so far? Any question? Okay. So I think it should be clear, right? So if you understand the key point, right? Like, wait, what's going on here? Okay. So if you understand the key point is like static friction is from 0 up to a maximum. Question 10. Yes, that's my plan. Question 10 is the slab question, right? The incline. Yes, that's what I want. That's the plan. Okay, so let's go question 10. I guess everyone is fine with 9 now. So question 10 is another kinetic friction problem. Okay, so question 10. Let's bring up question 10. Question 10 is here. So in this figure, this is 0.5 kg, this is 2 kg, right? Alpha is 40 degrees. Here we only care about static friction is 0.6. And find the range of value where the box does not slide on the incline. Okay, first let us try to understand the situation first before I start figuring out the situation. Okay, so what I have here, right, is an incline. So let me show you with something. Okay, I have a inclined surface, right? So I have an inclined surface and I have an object. Okay, so according to this, the camera is too small. If I'm doing it in a class, you can see me running across the room, but you know, so I'm trying to show you what is happening in this question. So I have static friction here a little bit, but if I don't move and if I incline it, it will start to slide down. Okay, what this question is saying is that if I exert a force on the system, this system will accelerate. So if I make it accelerate, right, then there's a chance that this will try to stay on the surface. Okay, so it will stay on the surface if I accelerate. Okay, so I must be fast enough so that it will stick to the surface. But I cannot be too fast. But if I'm too fast, right, I'm too violent, if I push it with a force that's too strong, it will just make it go back over the surface. Right? So I hope you can imagine the situation. A mouse is too expensive, so I don't want to, yeah, this is better, right? So if I incline this, it will slide down. So if I accelerate a bit, if I get some motion, it will stay on the surface. Okay? But if I accelerate too fast, right, then it will just, if I accelerate too fast, it will just like go back, right? It will slide over the top of the surface. Okay? So so what I'm trying to say is that there must be a minimum force and the maximum force, right? Anywhere outside this range, it will start to slide, either slide down or slide up, right? It will not stick to the surface. So hopefully everyone follow the situation. Now let's try to solve this problem. Okay, before I begin, well, the first thing that I want to do is I want to calculate the total acceleration of the system first. That will be very useful. So the total acceleration of the system, right? If I treat this as an overall mass, then the total system will accelerate together, which means that my acceleration is given by whatever force that you're exerting divided by the total mass of the system. Of course, right? This is just Newton's second law. Okay. Now let's talk about two cases. Okay, so there's a case one. I was saying, case one. If my force is too small, right? Not if I push it too slow, not fast enough, smaller than some minimum number, then box will slide down. Okay, so this will drop. Okay. The other case, if it's too fast, if I exceeded the maximum, then box slide up. Okay, so on this surface, it will go this way. So it must be at the correct range, a sweet spot, that if I push it steadily, it will remain stuck to the surface because of the static friction. Okay. If the incline is moving too fast, what is the force pushing the box up? It will be no force. Okay, it will be clear when we answer this. So it's actually no force, and what's actually happening if it's the surface is moving too fast, right? There's no force acting on the box, but the bottom is because the bottom part is moving too fast. It's moving too fast, so it's the relative motion. Relative motion, yes. Relative motion. Okay, so so let's try to work this out. Okay, so let's solve case by case. Let's start with case one. Okay, so finding the minimum value. So finding F minimum. Okay, so this is when, let's consider the case where the box is almost about to slide down. Okay, and I want to find the minimum, right? So let's see what is happening here. The box is almost about to slide down, and right now I'm only drawing the free body diagram of the upper box, small m. Okay, so this is alpha, which is 40. This is big M, but I only want, right now I'm drawing the forces acting on this little m. Okay, so that's normal, right? There I have a weight and I have the normal force. Okay, so if I push this as the correct force, right, it will stuck to the surface, right? It will prevent this box from sliding down. The reason it's prevented from sliding down is because there exists a static friction acting in this direction. Follow so far? Okay, so these are the forces that is acting on this box right now. Now let's try to solve the system, and I will resolve my forces along these two directions. So let's do that, right? Firstly, the normal force, resolving it this way, I got n sine alpha. Resolving it this way, I got n cos alpha. My static friction, resolving it this way, I got static friction sine alpha, right? Because when alpha is 0, this is gone. And then my static friction here is static friction cos alpha. Okay, now let's look at the components. Also, right, to save time, I want to find the F minimum. So finding F minimum is when the force is equal to F minimum, right, then my static friction is equal to mu s times n. Am I right? So I will substitute mu sn straight away, otherwise it will take too much steps. So let's look at the y or the vertical components. So for the vertical components, my acceleration is 0, but what is the net force? So the net vertical force is, I will circle them. So these are the vertical directions and these are the vertical ones. So these are my vertical forces. So the net vertical force is n cos alpha plus the friction, right? So friction is friction sine alpha and is balanced by mg, and I got the total acceleration, which is 0. Okay, and I'm saying that we are looking for F equals to F minimum, then the static friction is equal to mu s times the normal force. So I got n cos alpha plus mu s n sine alpha. This is 0. I bring this term to the right, it becomes mg. Okay, then I can actually factorize the n now. So I got cos alpha plus mu s sine alpha, and this is equals to mg. So this is my equation 1. Okay, so this is my equation 1, and I can get a second equation if I look at the x components. So x components, my acceleration, well, the system is accelerating at a, and what was my a? We have calculated the horizontal acceleration here, which is f m plus big M. Now, what is the net horizontal force? So I circle my vertical force, so I will square my horizontal force here and here. Only 2. So the net horizontal force is forward sine alpha minus the backward force cos alpha, and this is equal to MA direction, MA times x direction. But so I plug this in, and then same thing, right? When F is F minimum, the static friction becomes this formula. So this formula now becomes n sine alpha minus mu s n cos is equals to mf small m plus big N. I can actually factorize the n here. So sine alpha minus mu s cos alpha is equals to mf over m plus big M. Yeah, that's it, right? So this is equation 2. Okay, so I got 2 equations with 2 unknowns, right? I want to find f. Okay, so f for the minimum f, and this n is unknown, but I can cancel them if I divide the 2 equations. So let's divide the 2. So taking equation 2 divided by 1, okay, what happens on the left? This divided by this, I got sine alpha minus mu cos alpha. Then this is cos alpha plus mu sine alpha. And then on the right, the little m will cancel. So f, the little m cancel, and then becomes gm plus big M. So I can actually calculate my f minimum now. F minimum is g small m times big M, and these are expressions, but we are given the value, so we can actually plug in the numbers to get the number out. Cos alpha plus mu s sine alpha. Okay, so remember, right, we are given m is 0.5, big M is 2 kg, mu s, what's mu s? 0.4, right? And then you can check lah, it's 40 degrees. So I can put in all these numbers, and then I can find my minimum force. So my minimum force, if I punch out the numbers, is 3.90 newtons. Okay, so that is my my minimum required force. Okay, so does everyone follow our calculation so far? Okay, any question? So no one asking question. Does that mean you guys understand? Okay, so you understand what I'm talking about? So I found the minimum force, right? We still need to find the maximum force. So what's the maximum force? That is case 2. Slow a bit. Yeah, so that's why I stopped. And so do you want me to repeat any part? So let me write. Yeah, so tell me which part I should repeat or re-emphasize. Equation 1 and 2. Okay. Equation 1 and 2 is just free body diagram lah. So I think, yeah, everyone agrees with my free body diagram, right? There's 3 forces acting on it, and then I resolve following these 2 direction. Okay, and then for the y direction, so the y direction, there's no vertical acceleration. So the y direction, what is the net force? Okay, so the net force is, you look at the vertical directions, right? So it's all these forces acting here, and then from here it's just simplifying only lah. So nothing, no new information in going from here to here. I'm just moving the terms around. Okay, but the main point is these are the vertical forces. Then the horizontal forces. The horizontal force, we have a horizontal acceleration. We calculated just now, is F over this mass. Okay, and what are the horizontal components of the forces? So only 2 of them, right? This is the forward horizontal force. This will contribute the backward horizontal force. Okay, so it's the forward force minus the backward force equals to ma, right? And then I plug this in, and then again from here to here, don't worry if it was going fast, because no new information, it's just moving the formula around, right? So from here I'm moving the formula around, I get equation 2. Okay, then after that I divide equation 1 by equation 2. I finally got the formula like this. Oh, okay. Ax is not 0. Okay, so no need to repeat, but a bit rush. Okay, so I don't need to repeat, but someone asked Ax is not 0, is A. My handwriting is very bad. It's the A that we calculated just now. My A looks like a 0. Okay, okay. Okay, so next thing is case 2. Now, actually case 2, right, is basically repeating the whole calculation, but there's only one tiny difference. Okay, so this time I will try not to rush. So case 2 is, I'm pushing it quite fast now. Okay, if I'm pushing it like in a fast range, that means the static friction is preventing the box from sliding up. Okay, so it's preventing the box from sliding up, so the force, static friction now is acting this way. Okay, and then the weight is still there, then the normal force is still there. Okay, and so the rest is all the same. Okay, in fact, since the rest is all the same, right, I can recycle my formula. So what am I talking about? So what's the difference between this picture and this picture? Right, ignore the later one, the red color pen. Right, So everything is the same, only that my static friction now is pointing in the opposite direction, right? So the only difference between this picture and picture is the direction of the static friction. So that is the only difference. So this direction is the negative of this direction. So I want to save time, right? I'm lazy to write so many things again. So the only difference is this is opposite. So what I can do is I can recycle my calculation, right? You can confirm by doing the full calculation. This part is changing sign, this part is changing sign. Okay, so what I'm going to do, so if you repeat the same calculation, right? So repeat the same calculation, you will get a similar formula, right? Because I will get the same formula as above, but I will change sign. So now it becomes a plus, and down here becomes a minus. Okay. My God. Okay. So everyone follow so far? So similar calculation. Okay, but I just changed the direction of the friction. You can do the similar calculation. In fact, if you are not very confident with this question, so try the calculation and try to get this. Okay, if you can't, come and check with me. But if you understand what I'm following, right, then what I'm doing is just change the direction of friction. So change the direction of friction, I just change anything related to the friction. Then if you change, you just get this. Okay, so if you plug in the numbers, you will get the maximum force, which is 71.0 newtons. Okay, so now we got the maximum and minimum force. That finishes our answer already. So in other words, for the box to remain on the surface, okay, my force must be between these two numbers. Okay, must be greater than 3.9 and less than 71.0 newton. Any less, if my force is less than 3.9, it will start to drop down. If my force is greater than 71, it will start to slide up. Okay, and relative motion, right? So yeah, because of there's no force to push it up, but it's just relative motion. It's sliding up relative to this box. Okay, any question? Okay, so okay, so if there's no question, then that's it. Or any part that is not clear, I did not notice I was rushing just now, so that's why, right? So which part wasn't clear? Okay, so the key point is to draw the free body diagram, right? And the question, just reading the question itself, maybe like by itself it looks a bit scary and it sounds like complicated, but if you actually see what I was doing, right, I was just following the rules that we always been following last time. Draw free body diagram, get the forces, F equals to ma, vertical and horizontal components, right? From this equation we can get our answer. So the key point is the rules that we follow, right? Free body diagram, get the forces, resolving the forces, do everything correctly, then that will get our answer correctly. In fact, we did not introduce new forces, right? It's normal force, static friction, kinetic friction, and things like that. So everything is following the stuff that we learned in the lecture. So it's supposed to be nothing new here, right? Just that we need to remember to apply the formula correctly. That's the key point, right? Correctly. Okay, so it's more clearly. Okay, good. I'm recording. Yes. Okay, so it's more or less time already. So I think, yeah, that's the rest. I think everyone is okay, right? You can do the question. Maybe later this week I will upload the solutions for tutorial 2 now. Okay, so otherwise there's not much time to start a new topic. And for next, so next time we meet on the Monday, we will continue about the potential energy. So we are not finished about potential energy yet. Okay, so far I have shown you the potential energy formula is this. You have seen before. A lot of high school have taught this before, and now we sort of know the reason why, I guess, using calculus now, right? So now you guys are learning calculus, or have already learned it for math students, and we are applying it to work it out here. Okay, and so our next class is Monday. We shall continue to talk about potential energy on Monday, and also on Monday we will continue talking for non-conservative force. These are conservative forces. Okay. So I think that's all for today. So if there's no other question, then we can end the class now. Let me stop recording. Right. So stop recording.